Kyoko Awaren works on the compressor assembly line at a refrigerator factory. The compressor is the heart of a refrigerator, and Kyoko puts together the crankshaft and upper bearing for this very important component. The crankshaft and upper bearings are forged by a subcontractor and delivered as required to the refrigerator plant. A compressor consists of about 60 parts, which are assembled by 250 processes. Numerous holes must be made. Every surface must be polished. Each part requires a high level of precision, on the order of 1/10 of a millimeter or even 1/100th of a millimeter. The parts that Kyoko receives for assembly are all supposed to be of high precision and high quality. She finds, however, that 1 in a few thousand parts, or sometimes 1 in a few hundred, do not meet the required standards. A hole may be too large or too small, or the part lacks a hole altogether or is unpolished. Kyoko puts the defective parts aside so that they will not adversely affect the function of the finished compressor. She is worried, however, that some of the parts she found acceptable may be rejected at a later stage of assembly or processing. She begins to wonder why all these defects are made and how to eliminate them. Experience tells us that inspection does not necessarily guarantee the quality of a product. The key to quality control lies in the manufacturing process itself. Defective parts result from lack of precision or incomplete processing. The important thing is to minimize dispersion in the quality of parts. What kind of approach and methods do we have to find the cause of dispersion and assure uniform quality?
Japanese methods of quality control have met with great success. And I believe the reason for their success is that we have several effective tools of quality control. Statistical quality control, as it was invented in the United States, is too complicated for most people. After it was introduced to Japan almost 40 years ago, it was made accessible to anyone through the development of the tools of QC, which are called the 7 tools in Japan. One of the best-known features of Japanese quality control is the study group called a QC circle. A QC circle is made up of several people who get together to discuss and devise ways to improve quality and productivity. You might think that all you have to do is form a group to achieve results. But that is not enough. All the members of the QC circle must be able to use the tools of quality control. History has shown us that tools and instruments are of great importance. For example, Galileo discovered the rings around Saturn only after he had improved a refracting telescope for astronomical use. He could not possibly have made the discovery without an instrument that acted as an extension of his natural eyesight. Similarly, Japanese quality control would not have been successful without the histogram, PARETO diagram, cause and effect diagram, control chart, correlation chart, checklist, and other tools. Let me explain each of these tools one by one. The first is the histogram. When you manufacture a product, you always aim at a certain range of quality. Those products that fall outside that range are defective. The histogram shows the number of units that deviate from the target quality and the degree of such deviation. The vertical axis indicates the number of units, while the horizontal axis represents a selected characteristic of the product. The majority of products conform to the target, but some products are slightly off target, either lower or higher than the standard required. When all our samples have been plotted, the histogram is complete. Now we indicate on the histogram the upper and lower limits of the standard. All units that fall outside the specifications must be considered defective. You can eliminate such defects either through inspection or by fixing them. These are the only ways in which to deal with the defects and bring products within specification. However, the greatest value of the histogram is to show the degree of deviation from specifications. So, a histogram should be drawn up for all measurable characteristics, such as weight and dimensions. You may wonder how many products to sample. The best number is between 50 and 100. Less than 50 will not produce an explicit histogram, but over 100 will not change the results appreciably. That, in brief, is how we construct and use a histogram.
The first step in problem solving is to gain a thorough understanding of the work situation in the factory and the dispersion in the quality of output. Wherever there are defects, there is a problem of dispersion. Once a problem is recognized, it's necessary to find its source.
This is where the second of the tools of QC, the PARETO diagram, proves very useful. In the manufacturing process, there may be various reasons for a defect, but what we need to know is the major reasons and how they rank in importance. You construct a graph listing the various sources of defects on the horizontal axis and the number of defects of that description on the vertical axis. The source of defects should be written in order of frequency from left to right. The result is a PARETO diagram. This is an example of a finished diagram. Here, the most frequent cause of defects is errors in the design drawings. The next most frequent cause is insufficient communications among the people involved at various stages of the manufacturing process. And the next, labour disposition errors. There are various other causes listed on the chart, but they are relatively minor, and eliminating these will not affect the situation greatly. In order to reduce defects, we must first tackle the major causes. Referring to the diagram again, we note an interesting common factor among the top three causes: design errors, poor preparation, and labour disposition errors. They all involve human error. The next question is, who is actually responsible for these errors? With some investigation, we found that certain individuals were responsible for the great majority of the mistakes. Greater care by those people alone will bring about a substantial decrease in the number of defects. As you can see, by clarifying the main causes of defective products, we can learn where best to direct our energy. This is the special contribution to QC made by the Pareto diagram.
Using a Pareto diagram, it's possible to discover the most frequent sources of error in the production process. These are the areas to be concentrated on, since they have the greatest effect on product quality. We now seem to be one step closer to the source of dispersion. But we still haven't located the root cause. And this is the next task, to look for the problems that lie behind the problems. The parts handled by Miss Awaran have gone through numerous processes before they reach her. They have been handled by people, processed by machines, and moved around. Either the materials or equipment used in processing could be faulty. With so many possibilities, it's like looking for a needle in a haystack.
Next, let's look at the cause and effect diagram. From the Pareto diagram, we were able to clarify the principal causes of defects. Now we must uncover the sources of these problems. Because there are so many possibilities, anything from human error to materials, it is best to get together as many people as possible to discuss the reasons for the problems uncovered so far. A tremendous amount of information will come out of such discussions, and a way must be contrived to organize it. The cause and effect diagram is an efficient way of doing this. On the far right, we write in the goal. In this case, it is eliminate manufacturing defect. Everyone will have different ideas about how this can be accomplished. These are organized by classifying them into groups and writing them in along the spine of the chart. You can see why this is sometimes called a fishbone diagram. When the chart is completed, it should, if at all possible, be posted on the factory floor. Some workers may have other ideas after it is posted, and these can be easily written in. In fact, the more ideas the better, since the major cause will not be found out unless every possibility is noted.
Once all imaginable causes have been noted on the cause and effect diagram, the most likely ones, the major causes of quality dispersion, can then be clarified. One thing that caught Miss Awaran's attention was the fact that the defect rate seemed to vary from day to day. On some days, there were no defects at all. Here may be a helpful lead to the real culprit in this case.
One of the most valuable clues in tracking down the causes of dispersion is some change in the course of time. Analyzing the incidence of the problem is most important. It helps to create a graph with the time span on the horizontal axis and the results we want to examine on the vertical axis. This can help us uncover various possible causes. Let me give you a concrete example. In recent years in Japan, the birth rate has gone down and the number of elderly people is on the increase. When this phenomenon is plotted on a graph, the results are quite striking. Here, as you can see, is a sudden dramatic drop. This point coincides with an unlucky year in the ancient Chinese calendrical system called Hinoe-uma, or the Year of the Fiery Horse. Recurring in a cycle of 60 years, this year is said to spell bad luck for any girls born then, who are said to be inclined to a fierce and unpredictable temperament, and thus to have difficulty finding husbands. It is hardly surprising that parents tried hard not to bear children in that year. That one year notwithstanding, the decline in the birth rate has continued steadily over the last 4 or 5 years. People have realized that small families are better for many years, and yet, as we can see from the graph, the decline is fairly recent. So what is the real reason for the decline in the birth rate? While searching for the answer, we located another very similar graph. This graph shows the marriage rate in Japan over the same period. And when superimposed on the birth rate graph, it is remarkably similar. It suggests that the reason for the recent decline in the birth rate is actually a decline in the marriage rate over the same period. A chart like this, with time on the horizontal axis and some factor along the vertical axis, is called a control chart. Although it was originally developed for production control, it works extremely well as a tool of QC. Another way of finding relationships between different factors is to plot one factor, the marriage rate for example, on the horizontal axis, and another factor, the birth rate, on the vertical axis. This is called a correlation chart or scatter diagram. The completed chart looks like this. As you can see, the plotted points correlate closely, forming one straight line. The exception is the one point where the two factors have no correlation, the year of Hinoe-uma. The tools of quality control include the control chart and the correlation chart. In quality control, it is essential to find out why defects occur. Otherwise, there is no way of eliminating them. In looking for the cause or causes, the first task is to collect data. This produces a massive amount of information which can be quite difficult to cope with. We can organize this data using the various kinds of graphs and charts introduced in this video. Correct interpretation of the charts is also very important. In the example of the birth rate, it is unwise to jump to the conclusion that the decline is the result of the small family. After correlating the graph with other data, we learn the real reason, the decline in the marriage rate. The success of Japanese quality control, as we have shown, is not based on complicated statistical calculations. Statistics are handled using the tools of QC, simple charts and diagrams that can be used by anyone. QC circles are not, therefore, just groups of people sitting around discussing ways to eliminate defects. They gather and organize data in various ways and discuss the results. Their efforts bring to light many things they may have previously overlooked, leading to a clear understanding of the root cause. The tools of QC are therefore central to Japanese quality control.
ここに7つ道具の重要性があるということがお分かりになったと思います。
The tools of quality control are procedures for problem solving. They lead the way to a complete understanding of the situation. The general pattern of dispersion in quality is revealed by a histogram. The sources of problems and their relative importance is revealed by a PARETO diagram. Problems occurring on the work site are charted on a cause and effect diagram. The time factor in defects or abnormalities is explored using a control chart. To determine the underlying causes, the best method is to plot the data using a correlation chart. In these ways, the information obtained in the workplace can be organized, displayed graphically, and analyzed accurately. The tools of QC are very effective in problem solving and one of the most important features of Japanese quality control.